Okay, today's topic, if you look through the notes, you're going to like this one because there's no calculations, there's no math, and more or less it's a bunch of pictures as I describe a concept to you. I thought this was a good Friday topic. There's no twist. Well, I want to actually start with a little bit of a, preamble. Physics is in my opinion, one of the coolest sciences because we're not done learning about physics. I think you could argue in other subjects that maybe especially say social studies, you study history in the past maybe you study about the present a little bit. Physics, to a certain degree, a lot of physics still has to be discovered though. There is so much about our world that we cannot explain. I can give you tons of examples. We hardly understand how light works, how gravity works, how black holes work. And today's topic, I'd like to give you an example of something that happened not even that long ago, where physicists did not understand this concept until all of a sudden something catastrophic happened, and we had to go out and try to learn more. And to be honest, I don't fully understand this topic. That may sound kind of weird. I'm trying to teach you something that I understand the basics of, but I don't fully get it, if that makes sense. And a lot of where physics is going to go, especially in Physics 30, I struggle with that because as a teacher, I want to feel like I know everything. I can't, because to be honest, even the smartest minds in the world don't know everything about some of these topics. So, it's kind of cool. It's kind of humbling to be like, wow, there's so much more to learn out there. And that's this topic on resonance. So, where should I start? Here's what we do know about resonance so far. Okay? Imagine that you're pushing someone on a swing. So, I was outside a couple days ago pushing Kinsey out on the swing. Back and forth and back and forth. She has frequency and period. Hello. Okay. Okay. If you're going back and forth on a swing, you'd have frequency and period, because essentially she's like a pendulum. Does that make sense? Okay. Well, the question I ask here is, what happens if you want to keep them moving? Because if I just push Kinsey once and let her just go back and forth, she'll swing for a while, but she'll eventually slow down and stop, right? Why does she slow down and stop? Friction. Yeah, friction eventually takes place, right? So you guys probably know this because you've all been on a swing before. If you pump your legs, or if you have someone push you, you can keep going in that same motion for a really long time. Is it easy to keep someone on a swing that's already going, keep them going? I would say, yeah, it doesn't really take much effort. When I'm standing there pushing my daughter, I can kind of some parents, on your phone. Yeah, go sweetie, go. Because it's not really that hard to push a kid when they're on the swing. And that's my point here on the first slide. What applied force do you need to keep them moving? Not much. Just enough to overcompensate for friction. Does that make sense? Yeah. Well, what we're actually describing here is what's called resonance. If you want to make them go higher, you have to push at the right time. Okay? For example, if Kinsey's coming back here, if I push right at that right moment, I can give her more momentum to get going better and better. But if Kinsey's at this moment here and then I try pushing her, it doesn't really work all that well. And I think most people kind of figure this out when they're really young. There's a rhythm to this. And if you push at that right point, things are going to work properly. Does that make sense? So here's some terms I need you guys to know. I bolded all of them. The first term is called a resonant frequency, and it's sometimes called a natural frequency. As Kinsey's on the swing, swinging back and forth, she's got a natural frequency. Okay? That's happening without me doing anything. The forced frequency is when I push her. If the forced frequency matches the resonant frequency, the swing goes higher. Does that make sense? So Kinsey's going back and forth according to her own little pattern. If I push her, I'll do this then too. If I push her at the right time, if my pushed frequency matches, she'll start going higher. Okay? But what if I try pushing right there or here? Then my forced frequency and her natural frequency are not in sync, and then things don't work as well. Okay. For those of you guys in my math class, this graph here should look fairly familiar because we're talking about sine waves right now. One of the terms that we've been talking about in math is called amplitude. This distance right here is called an amplitude. Okay. You guys see how there's two waves here kind of overlapping each other? Okay, so there's like one right here and one right here. At this particular moment right here, do you see how these two waves are like in sync with each other? Well, the way that waves work then is if they're in sync with each other, it actually causes them to like grow. And so this wave and this wave would actually grow and cause an even bigger wave. And so that's the idea behind Kinsey was going like this. I pushed her like this, and so therefore the wave becomes even larger than it would have been normally. Okay. So we have a name for that. It's called mechanical resonance. That makes sense? Long story short, vibrations get bigger. Amplitudes get larger. And what I'd like to do is show you a bunch of examples of resonance that we figured out that you probably have heard of before. So here's the first one. Musical instruments rely on mechanical resonance. Say you were to play, I'll use a guitar first. Say you were to play a guitar. Really, a guitar involves a string getting plucked. And if you just pluck one string on its own, yeah, it'll make some sound as it vibrates back and forth. But what really gets the sound going is the mechanical resonance with the body of the guitar. The body of the guitar will then pick up those sound waves and amplify them, making them bigger and louder so that you can actually hear the guitar from the other side of the room. Does that make sense? Most musical instruments operate on this sort of principle. Here's a French horn, same sort of an example. As you blow into the instrument, you're causing vibrations inside this instrument. That's fine. But we really need to find a way to amplify it so that it's actually loud enough for someone to hear. Again, this is where my shortcomings come in. I don't know the exact science behind how a French horn works. But like, I get the basic principle. It probably makes sense that you want to have some sort of, I don't know, funnel on the outside here so that those vibrations can be amplified louder and louder. Here's another example. Anyone know what I'm going for in this picture? Yep. Maybe you've seen this before. The idea that if an opera singer, for example, sings at exactly the right pitch, they can break glass. This is actually true. It's not like some sort of fake thing that can happen. Every single object has natural frequencies involved. If you were to hit the exact right pitch that this glass has the natural frequency of, it would cause the glass to start vibrating more and more and more. And if you get it to vibrate enough, it will actually shatter the glass. It's the exact same concept as how Kinsey is going back and forth on the swing. If I push her hard enough, I could cause her to go flying out of the swing. That's what's happening to the glass here. The glass has its own natural frequency. As it sits there, it doesn't look like it's doing anything, but it actually is vibrating. I mean, you can't see it, but I mean, at a molecular level, if you were to zoom in, you would see molecules slightly moving and vibrating. For those of you guys in my chemistry class last year, we talked about something called translational motion, rotational motion, and vibrational motion. Those terms sound familiar? Okay. So everything does vibrate naturally. If you can get this thing to vibrate more and more and more, you could shatter glass. This is the example I like to do today in class. I'm going to turn the video camera so you guys can see this, I hope. Some of you guys have noticed these boxes sitting around here. These are called like tuning forks. And so if I were to hit this thing right here, it has a natural frequency as well. And if I get it vibrating, it's going to make a sound, which maybe you can hear from where you're at. A little bit, right? So this thing is vibrating enough that it produces an audible noise, but not enough that you can hear it back there. Well, this particular one right here has a box built around it, which is hopefully going to amplify those waves and make them louder. So that when I hit it, I didn't hit it very hard, but like you can hear that no problem, right? Exact same force on this guy. Does that make sense? So this is the exact same property as like a musical instrument has, where it's got some sort of box like a guitar meant to amplify things. Well, one of the cool things about these ones, if you mess around with these, is that both of these are tuned to have the same frequency. It's not labeled on them, unfortunately. But any of you guys in like band know music? Okay. This one right here says this is a G, which is like one of the notes on an instrument. So this is actually a pitch based on how many hertz it vibrates at. Hopefully this works. What I'm going to do is I'm going to strike this one right here. Okay, now I'm going to dampen it. Can you still hear that? This one is now vibrating.
So like transfer it over to that one? Like
Yeah. So this one is vibrating at whatever frequency it vibrates at. I gave this one a forced frequency, which is now forcing its frequency onto this guy. This guy has a natural frequency. It wasn't vibrating very much, but the sound waves coming from this one cause this one to now start vibrating more. Yeah, waited too long. And you can hear it moving. Hope this works here. These two have different pitches.
Susan Stack, can you please call 100?
Do you guys hear how they're slightly off? They're close to the same pitch, but they're not the same. I hope this works. If I hit this guy now, this one's not vibrating.
Has to be the same pitch.
It's not the same pitch. They don't have the same natural frequency. Does that make sense? But I changed this one out for this one. It is still echoing. Check.
With the, like on the first slide, or the second slide, with
The glass breaking?
no,
No, the one before it.
where the force frequency matches does it have to match exactly?
I think so, yeah. This is where I hate this unit. I love it, but I don't know enough about it. Here's my understanding. Waves, when they have that up and down motion, if they're in sync with each other, like that one picture I had there, it'll cause the wave to become elongated, like taller. And so it is possible that you could have like a frequency that's like half of the other one, and then that could still help to like partially make it louder. If that makes sense. There's a term, I need to research this more, it's called overtones, where like, if you know anything about music, octaves operate like a low C and a middle C and a high C, all kind of operate on kind of the same frequency, except like the wavelength and the period is either like doubled or tripled or halved. If that makes sense? I don't know if that fully answers your question, but I think the answer is like, maybe. I think it's possible. Sorry. I don't know nearly enough about how this stuff works yet.
What are these called?
These guys right here, these are tuning forks that are attached to a box, so that the box can help resonate the wave a little bit better.
Okay, so I'm when we hear when you hit it, and then
This one.
it goes off into that one.
Well, and technically it's going everywhere, obviously, but a lot of sound is being put into this one, yeah.
And then we hear that because that's because of the two waves.
Well, what's happening is this one here is resonating waves out everywhere. Okay? Your ear is picking up those waves and you recognize it as a sound, right? But this thing right here has its own natural frequency as well. And as soon as that wave's hit it, it starts to get this guy moving just like the swing with Kinsey. So this guy right here is vibrating just a little bit. Those sound waves come in and start hitting it, and it starts vibrating a little more to the point where this one starts vibrating enough that you can actually hear this one on its own now too. Does that make sense? Maybe different example. For any of you guys in band, I notice this a lot whenever I'm playing music. If the snare on the snare drum is left on, and someone's not playing the snare drum, you guys know what that is?
Yes.
And then there's no one playing, but you can actually, like, far away, like the rest of the band is playing, sometimes you can hear the snare rattling a little bit. Ever experienced this? And you have to like pop the little switch down. What's happening is all of those different frequencies that the band is making is causing that to actually vibrate enough that it makes it so the snare is actually making some sort of noise when we really don't want it to. Does that make sense? Okay, let me turn this back around so you guys aren't facing no one. Okay, I'd like to show you guys an example. I forgot the date. This was somewhere in the mid-1900s. A bridge collapsed. This is the Tacoma Narrows Bridge. And it collapsed because of resonant frequency. You guys don't have this picture because I couldn't put it in here, but here's an animated GIF of what happened to this bridge. Okay, so here's what was happening. As this is not wind, by the way. Like, this is not like the windiest day in the world. But as wind and stuff like that was passing underneath this bridge, the frequency started to match the natural vibrational frequency of the bridge. And it started amplifying it to the point where the bridge started to sway back and forth. Now, if it was just wind would just push the bridge one direction and that would be it. but the frequency of the air molecules moving underneath the bridge caused the bridge to start shaking a little more, a little more, a little more, until it starts doing this, until eventually the bridge looked like this when it was done, because it absolutely collapsed. And this is what I was trying to start class with, the idea that, like, I don't think engineers and physicists really truly knew what vibrational motion and resonance could actually do to a bridge until the last 50, 70 something years, until all of a sudden one of these things breaks and you're like, how did that happen? Like, it was built so solidly, and just, it wasn't even like a really windy day. It just happened that the vibrational forces matched. Again, like the swing. And the swing just kept getting pushed further and further and further until, I mean, eventually it has to snap. Does that make sense? So, I don't know the math behind this. To be honest, there's probably only a few people who do. And they are highly trained engineers who have to figure out how to make it so that the vibrational forces of things like wind and cars and whatever is happening don't somehow match the vibrational forces of the bridge so that doesn't happen again. Cool job. And I don't know that though. I mean, if I did, I'd be in that job, obviously. So again, that's where, I mean, I like teaching this stuff, but this is a bit of a struggle. I know some stuff about it. I certainly don't know everything. So, but I mean, maybe that's what's cool about physics, is that's the point. We want to learn more about how resonance works. So. Okay, here's the good news. I'm really not going to test you on this. There's no math. There's no calculations, at least at this level. Right? I just need you to know the concept, because now you basically know what I do. The idea that if you have a natural frequency in an object and a forced frequency that you apply to it somehow matches it, it's going to cause that amplitude to become bigger. Amplitude in waves is what causes the waves to become bigger. Okay? And really that makes them louder, or it makes them more noticeable when they start swinging back and forth. So, that's it. Any questions?